Welcome back everyone. In this lecture I am going to give an alternating proof of this orthogonality of irreducible characters using only tensor products and dual representations. So basically it's the same proof, but we are going, because we developed the language, so we will be able to write it more systematically now using this language that we have developed. So let us actually start with this following proportion. So this is what the key point in proving the orthogonality. So what is the proportion? So we take actually any two finite dimensional representations of G. So let us call it V and W. This is finite dimensional representations of G. So then what one can prove? So then we have the inner product of the character. So this is exactly given by the dimension of the home G V comma W. Okay. So once we realize this, then it is clear that if we specialize V and W to be irreducible characters, then using Schur's lemma, this home space we know already it will have dimension either 1 or 0 depending upon whether V and W are isomorphic or not. So that actually proves the orthogonality of irreducible characters. Okay, so let us write down like a two-line proof of this using the tensor products and dual representations. So here is the proof. So let us recall what is the definition of the inner product of the characters. So the inner product of the characters given by, so you take this average sum summation over G in G, and then take this character values chi V of G and then chi W of G bar. So this is the definition of the inner product of the characters. So now let us rewrite this in terms of dual representation on the tensor product. So we already seen that. So this value is exactly the character of W star of G, and the product is going to be the character of the tensor product. So what we get? So let us go step by step. So this is exactly equal to 1 divided by the cardinality of G, G in G, chi V of G and then chi of W star of G. So now let us focus on this product, and this product is exactly equal to chi of V tensor W star of G. So basically what we got that the inner product chi V chi W is exactly equal to the average sum 1 divided by the cardinality of G times summation G in G chi of V tensor W star of G. So this is what we are getting as the inner product. So now if we just look at this term, what we have here, and this is very much related to this projection operator that we have already defined. So you look at this P, which is the cardinal 1 divided by cardinality of G summation G in G and sum over G in G, and this is lies in the center of the group algebra. So this is in the center of the group algebra CG, and this projection operator we already studied, and they are related to this character values. And what is the connection? This is something we have already observed, and this right hand side average sum is exactly equal to the trace of this projection operator when you apply it on this V tensor W star. So this operator is going to act on the any representation, given representation, you make it act on V tensor W star, then what you get, the trace of this is going to be exactly equal to this right hand side. So this is something already we proved long time back, and that we are going to use it. So now what is the trace? The trace again has many different interpretations. So you can actually if you look at the trace of this projection operator, you can actually identify this with a dimension of the G invariance vectors of this V tensor W star. So, basically this is given by the dimension of take V tensor W star of G. Okay. So, this is something again we have already proved. So, now what happens to these V tensor W star on the home space? We already know that they are isomorphic. So, recall if we take V tensor W star, this is exactly isomorphic to home W comma V over C, this home space as G representations. So, this is something we already know. Since the tensor product V tensor W star and the home W comma V, they are isomorphic as G representation. In particularly their G invariance subspaces will be equal. So, in particularly we will have this V tensor W star G is again isomorphic to the home G W comma V. So, this is something immediate from this isomorphism, So, that means the dimension of this V tensor W star G is indeed given by the dimension of home G W comma V. So, now if we put them together, we can see that the inner product is indeed given by this dimension. So, now if you start with this V and W to be irreducibles, using Schur's lemma, we can see that if W and are irreducible, so then the dimension of this home G V comma W or W comma V, so this is going to be either 1 if V and W are isomorphic or 0 otherwise. So, this is just Schur's lemma. So, if we use Schur's lemma, then as a direct application we get the orthogonality of these irreducible characters. So, this is much more conceptual proof, and then we are using whatever the language that we have developed so far in order to actually prove this. So, but to give this proof we need to know the language, so that is why I just postponed this to the end. Okay, so now I am going to actually leave one more important exercise about these home spaces and the tensor products. And indeed, like if you know the language of the category theories, so there are these two functors that you are actually able to define. One is the tensor product, the left product, and then like the home, again home functor. And basically what we are saying, we are going to say that these two functors are adjoint to each other. So let us not worry about the language of category and all, but let us simply write down what does it mean by saying something adjoint to something. So, in simplest language, if you take this V, W, U to be finite dimensional G representations, again let us say we are working over C. So, then you take this home space between V tensor W to C, some U, and look at all possible C linear maps. Okay, this is the home space between V tensor W to U. So, now what one can prove, this is indeed isomorphic to home of V comma. So, you can switch this W to the right side. So, this become home V comma home of W U, and this is again will be isomorphic to home V comma U tensor W star. So, basically what we are trying to say, this tensor W can be shifted to this tensor W star. So, that is what we are saying, and that is possible, and that does not make this isomorph different. Okay. Whatever objects that we are getting, they are all isomorphic. So, these isomorphism, they are all isomorphism as G representations. So, in particularly, so if you take for example one dimensional thing, you can see that the home of C comma V tensor W star. So, you can actually bring this W star to this C tensor W. So, then this is exactly equal to home C tensor W comma V, which is exactly isomorphic to home W comma V. So, this is the identity that we are getting. Okay. So, in particularly we can also specialize to the G invariant things. So, maybe write it as the third thing, it is immediate from the earlier observation. So, if you are looking at the home G and then W comma V, so which is isomorphic to, you take this V tensor W star and then take G invariance there, and which is again isomorphic to naturally the home G C V tensor W star. Okay. So, these isomorphism that you will have. So, if you are looking at all possible G invariance maps from W to V, so that is equivalent to saying that you look at all possible G invariance maps from C to V tensor W star. So, sometimes even though here what we are looking here is like you take this trivial representation C and then embed that trivial representation inside V tensor W star. So, that is what this demands. That problem is as equivalent as taking all possible G invariance maps from W to V. So, they are not indeed kind of two different problems. They amount to somewhat similar problems. Okay. So, this is more or less I want the things that I wanted to discuss about the tensor products, symmetric products and so on. And later what we are going to do, so we will also actually talk about tensor products over subalgebras and so on. So, that will be used in the definition of induction and so on. But what I will do first, I will define the induction in a more accessible way, then later I will use the tensor products to define the induction. So, that you will actually get comfortable with the induction first, and then later you will get more like advanced mathematical meaning of the induction as well. So, before that what I want to do is I want to talk about these group determinants. So, these are actually in a way motivated to invent this representation theory. So, let me briefly actually tell about these group determinants, and then I will also make some important remarks about how to factorize them and so on. So, then we will use the representation that we have developed so far to get that decomposition. So, this is the new topic called Frobenius determinant. So, let me define what they are. So, we start by enumerating the group G. So, we just list them. So, you take G and then just enumerate G1 etc., let us say Gn. So, now I want to maybe I will fix this capital N to be the number of elements. So, fix capital N to be the order of G, and then for simplicity we can take G1 to be the identity element. So, we just enumerate and then list all the elements as G1 etc. Gn. Now, what we do, we introduce n commuting variables indexed with the elements of G. So, we call them just xg1 etc. xgn. So, these are the commuting variables indexed to our G. So, now we are going to define a matrix, and the determinant of that matrix is called the Frobenius determinant or the group determinant. So, how the matrix is indeed defined? So, the matrix is defined as follows. So, people use actually two different way of defining the matrix. So, maybe I will use the notation that is followed in this book of Ettinghoff. So, we consider this matrix Xg, so whose Aijth entry is given by Xgij. So, this is the matrix whose, so it is basically indexed over this capital G, whose Aijth entry is given by Xgij, and the determinant of this matrix is called the group determinant or Frobenius determinant. So, the determinant of Xg, so this is the determinant or the group determinant. Okay, so let us actually see some examples and then it will become clear. So, what we mean by this? So, sometimes they also use this another way of writing the same determinant. So, sometimes they use as GH entry to be just X G inverse H. Okay. So, that also one can take it as the matrix entry GH entry, and then that matrix also one can actually consider. Anyway, it will not actually make too much difference here. This is basically depending upon whether we are multiplying by left or multiplying by right. So, we will see in a minute how this determinant makes sense and so on. Okay, so, let us actually look at this Frobenius determinant and then compute it for some smaller examples. So, if we take this determinant, so it is going to be polynomial in the variables xg1 etc. xgn, and what are all the immediate consequences? Okay, let us do some examples first. Okay. So, let us take for example G to be G modulo 2z, and then let us write this as 0 bar 1 bar. So, this is the list that I am actually making. So, in particularly the corresponding variables I am going to denote it as x0 and x1. So, now what is the matrix Xg? So, recall Xg is, so you have G1, G2 and so on, Gn, and here again you have G1, G2 and so on. So, if you take the ith row and jth column, so the entry is going to be here x g I g j. So, that is your matrix. Okay. So, then you can see that here what is going to be your indices 0 and 1. So, you have 0 1 and then 0 1 here. So then you take, for example, if you take the first row, you are multiplying with G1, so that is just identity. So you get xg1 xg2x. So this is going to be xg1 xg2 and so on xgn. So that is what you are going to get, x0 and x1. Now similarly, if you take this first column, you see that you will be multiplying xgi g1, again it is going to be the same xg2 xg3 and so on. So you get x1 here, and now it is going to permute. So 1 times 1 plus 1 is 0, so you get x0. So the matrix of this G modulo 2z is going to be x0 x1 and then x1 x0. So this is our matrix. So now what is the determinant of this? The determinant of this xg is easy to compute. It is x naught square minus x1 square, and this just factorize into x naught plus x1 times x naught minus x1. Okay, and this factorization is not accidental. So this has some very deep meaning in terms of representations. Okay, so that's what we are going to prove. So let's do one more example. So let's take G to be G modulo 3z. So then we want to compute. So let's compute the matrix here. So you have 0 1 2 and then 0 1 2 here. So as I said, the first row is 0 1 2 and then second row is again 0 1 2. So that like 2 2th position, so you have to add 1 plus 1, it is going to be 2, and then 1 plus 2 is going to be 3, which is 0, and then 2 plus 1 is 0, 2 plus 2 is 1. So basically the matrix xg is going to be exactly equal to x0 x1 x2 x1 x2 x0 x2 x0 x1. Okay. So actually it will be better to change the entry to be this x g inverse h, so that when we are looking at the diagonal, so we will be getting indeed the identity. Okay, so maybe let me slightly change the definition of the group determinant, and this is not going to affect anything much. Okay, but it is going to make our life simpler. So let's change this. So if you are going to take this GH entry to be x g inverse h, so then this is exactly GI inverse and then GJ. So this is what we are going to get. Okay, so this is the definition I am working. So in particularly xg will have identity on the diagonals. So that is what we want. And then if you take for example the first row, then G1 inverse is actually identity. So what you get is here xg2 etc xgn. Similarly, the first column you are going to get xg2 inverse etc xgn inverse. Okay, so this is the matrix that I am going to talk about. Here things are not going to change because it's a very small example. So we are going to get the same matrix x naught x1 x1 x naught. So it's going to be the same matrix. So now let us look at this G modulo 3z. Then here the things are going to change. So we will rewrite this. and we can see that so what we get, so we are going to put x G inverse H as the matrix entry. So then you have to just use this is the G direction, this is the H direction. So when G is 0, you get 0 1 2. Now when G is 1, the 1 inverse is 2, so you have to add with 2. So you get 0 0 here, and then you can see that you have to add 2 here, so you get 2 here, and then here 1, and similarly here you have to add 2 inverse, which is 1, 1 plus 0 is 1, and then here you get 2. Okay, so the matrix will be x naught, and then x2, x1, and x1, x2. So this is the matrix that you get. So the determinant, it is not very difficult to work it out. If you just use the determinant rule and then just write it down, what will be the answer of this. So maybe let's do this. So it is going to be x naught determinant x naught, x1, x2, x naught minus let's do it via this first row. Then this is x1 determinant x2, x1, x1, x naught plus x2, x2, x naught, x1, x2. So then what we are going to get? We are going to get x naught square minus x1, x2 minus x1, x2, x naught minus x1 square plus x2 square minus x naught, x1. So if you simplify, you can see that the determinant of xg is going to be x naught cube. So that is going to be come from this, and then plus x1 cube, and then plus x2 cube. So then minus, so you get x naught, x1, x2 here, and then x1, x2, x naught here, and then here 1 x2, x naught, x1. So there are 3 terms there you get, which is 3 times x naught, x1, x2. So this is the term that you are going to get as determinant. Okay. So now it is somewhat easy exercise to factorize this using the cube root of unity. So if you call this omega, let us say omega 3 to be the exponential of 2 pi I divided by 3. So then I will leave it to you to check this determinant of xg. So the determinant of xg when g is z modulo 3z. So this is going to be exactly equal to x naught x1 plus x2 times x naught plus omega 3 x1 plus omega 3 square x2 times x naught plus omega 3 square x1 plus omega 3 x2. So this is what you get as a decomposition of this determinant. So this already suggests that there is some kind of deep meaning in terms of the factorization of this group determinant. Indeed, it was first observed by Dedekind that for any finite abelian group, we have the determinant of xg as product of this linear polynomials xg. So maybe let me state the Dedekind theorem. So which says that if G is finite abelian group, then what one can prove, you take this determinant of x g, so which is a polynomial in all these variables x g, g and g, and this can be written as product of, you run it over all possible one dimensional characters from G to C star. So, this is the group homomorphism, so which is also denoted by G hat, and then you sum it over all possible this chi G x G, where G and G. You take these linear factors, you take the multiplication of all of them, then you get exactly the determinant of x G. So, that is what happening here. Okay. So, if you want to rewrite this in terms of G hat notation, chi comes from G hat, which is the dual group, and you just take the linear polynomial on these generators x G, G and G, and you take the product among them, then you get exactly determinant of x G. And this is what Dedekind proved first, and then later Dedekind expected something more than this would happen for the general non-abelian groups as well. So, then he wrote a letter to Frobenius containing the definition of the group determinant and the factorization in the abelian case. So, he hinted that after doing some computation in the non-abelian case, which was actually done for some smaller examples. So, without including them, he mentioned to Frobenius that something similar should happen for any non-abelian groups. Okay. So, this is indeed the very first motivation to invent representation theory. So, Dedekind's question kind of motivated Frobenius to look for the factorization of these group determinants, and then he realized that this character theory can be used. For example, here we already have, you see, characters of the irreducible representations of finite abelian groups. So, naturally we will be replacing this G hat by more general characters of irreducible representations of more general non-abelian groups. So, then there will be some polynomial coming from them, and then we will be able to write this determinant of x G as product of those polynomials. So, maybe I will state Frobenius theorem in the next class, and then I will prove the Frobenius theorem on these group determinants. I will stop here. So, with this motivation. Thanks.